Hi, this is Will Murray for Educator.com, and we're talking about trigonometry, and we're finally ready to learn about the tangent and cotangent functions. We've been alluding to those in some of the earlier lectures, but this is the lecture where we're going to formally define what the tangent and cotangent mean and really get some practice with them. So the definition of tangent is very simple. It's just tangent is, by definition, the tangent of an angle is sine over cosine. And of course, you can only talk about that when the cosine of the angle is not 0. And so if cosine of a particular angle is 0, we just say the tangent is undefined. And the cotangent is just the same thing except you flip them the other way up. So the cotangent of an angle is cosine of theta over sine of theta. And if the sine of theta happens to be 0, then we say the cotangent is undefined. Now, the master formula that I've already mentioned before in a previous lecture for right triangles is SOHCAHTOA. And you can just remember the word SOHCAHTOA, or there's a little mnemonic to help you remember that if you want. It's some old horse caught another horse taking oats away. So if that's easier for you to remember than SOHCAHTOA, then by all means remember that. But the key point is that this tells you, this SOHCAHTOA formula tells you how to interpret the sine and cosine and tangent of an angle in terms of the lengths of sides of the right triangle. So I've drawn a theta down here in one of the angles of a right triangle, and then we talk about the side adjacent to theta and the side opposite to theta, and then the hypotenuse of the right triangle. And the master formula that you want to remember is that the sine of theta is given by the opposite side over the hypotenuse, the cosine of theta by the adjacent side over the hypotenuse, and the tangent theta, which we're learning about today, is the opposite side over the adjacent side. Let me run over the common values of the tangent and the cotangent function. And really the way to remember these is to remember the common values of the sine and cosine. Because remember, tangent is just sine divided by cosine, and cotangent is just cosine divided by sine. So if you can remember the common values of sine and cosine, you can always work out the common values of tangent and cotangent. So I've listed the common values in the first quadrant here. In degrees, we have 0, 30, 45, 60, 90, and those correspond to radians of 0, pi over 6, pi over 4, pi over 3, and pi over 2. And you should really have the sines and the cosines of these angles memorized and be able to reproduce them very quickly. And if you can, then you can immediately figure out the tangent and cotangent without really having to memorize anything extra. So for 0 degrees, the cosine is 1 and the sine is 0. Tangent is sine over cosine, so that's 0 over 1, just gives you 0. Cotangent is cosine over sine, which would give you a division by 0, so that's why we say it's undefined. For 30 degrees, the same as pi over 6 radians. The cosine and sine are root 3 over 2 and 1 over 2. Tangent, if you divide those together, you get 1 over root 3. And if you rationalize that, that rationalizes into root 3 over 3. So that's the tangent of pi over 6. Cotangent, if you divide them the other way, cosine over sine, you just get root 3. For 45, the cosine and the sine are both root 2 over 2, so the tangent and the cotangent are both 1. For 60 degrees, or pi over 3, you just get the opposite of what you had for 30 degrees, or pi over 6. So the tangent turns out to be root 3, and the cotangent turns out to be root 3 over 3. And for 90 degrees, or pi over 2, the cosine and sine are the opposite of what they were for 0 degrees. And so the tangent is undefined and the cotangent is 0. So the values that you get for tangent and cotangent, they're 0, 1, root 3 over 3, root 3 and undefined. So those are the common values you get for tangent and cotangent. And so when you have one of these common angles, one of these multiples of pi over 6 or pi over 4 in degrees, that's 30 degrees or 45 degrees, it's really, when you want to know the tangent or cotangent, you know it's going to be one of these common values, and it's just a matter of figuring out which one. So it's good to remember that these common values come up over and over again, because then when you're working out values for any particular angle, you expect it to be one of these common values. There's a couple more facts that I want to talk about, uses for the tangent function. One is that the slope of a line is the tangent of the angle that the line makes with the x-axis. So let me try to draw that. Suppose you have just a random line in the plane like this. What I'm going to do is look at the angle, theta, that the line makes with the x-axis. And now I'm going to move this line over. I'll draw it in blue, the translated version, over to the origin. So that's meant to be a line with the same slope, but just moved over to the origin. And if I make a triangle like this, we still have theta in one corner of the triangle. And the adjacent side is equal to the amount that the line is running over. So that's the run. And the opposite side is equal to the rise that the line makes in that triangle. So if we remember SOHCAHTOA, tangent of theta is equal to the opposite side over the adjacent side. That's the TOA part of SOHCAHTOA, which is equal to the rise over the run, which is equal to the slope of the line. So that tells you that for any line, the tangent of this angle theta that it makes with the x-axis is equal to the slope of that line. Another thing that you want to remember about sines and cosines is that once you know the common values of tangent and cotangent, if you remember which quadrants the sine and cosine are positive and negative, you can figure out which quadrants the tangent and cotangent are positive and negative. So let me label the quadrants here, 1, 2, 3, and 4. And let me label the positive ones. Remember, sine corresponds to the y value, so sine is positive in the top two quadrants, negative in the bottom two. Cosine corresponds to x values, so cosine is positive in the first quadrant and in the fourth quadrant, and negative in the other two quadrants. So if you want to figure out when is tangent positive, well, it's positive either when sine and cosine are both positive or both negative. Remember, the tangent is equal to the sine over the cosine. So tangent is going to be positive in the first quadrant, negative in the second quadrant because sine is positive, cosine is negative. Tangent is positive in the third quadrant because both sine and cosine are negative. And tangent is negative in the fourth quadrant because cosine is positive but sine is negative. So if you put these together, tangent is positive in the first and third quadrants, negative in the second and fourth, which is kind of the origin of this mnemonic that you can use to remember. ASTC, the way you remember that is all students take calculus. That stands for all of the sine, cosine, tangent functions are positive in the first quadrant. In the second quadrant, only sine is. In the third quadrant, only tangent is. And in the fourth quadrant, only cosine is. Now, you might wonder, how does cotangent fit into all of this? Well, cotangent, remember, is just the flip the reciprocal of tangent. Tangent was sine over cosine. Cotangent is cosine over sine. So cotangent is going to be positive whenever tangent is positive. It'll be positive in the first quadrant and in the third quadrant. So now we know our common values of tangent and cotangent. Remember that 0, 1, square root of 3, and root 3 over 3. And we know which quadrants it's going to be positive or negative. We can work out the tangent and cotangent of any angle, any common angle around the unit circle. So let's try some problems now. Let's start out by drawing graphs of the tangent and cotangent functions, and we're going to label the zeros and asymptotes of each and try to figure out what the periods are. So I'm going to start with the tangent function, and I'll do that one in blue. Okay, for the tangent function, I know that the tangent of 0 is 0, so I'm going to put a dot at 0. Let me mark my axes a bit. Pi over 2, pi, 3 pi over 2, 2 pi. Tangent starts out at 0. The tangent of pi over 2, the tangent of pi over 4, we said is 1, so let me put a dot there. And then when tangent gets close to pi over 2, remember that's really getting close to dividing by 0, so it goes up to positive infinity there. So tangent has an asymptote at pi over 2, and it goes up to positive infinity there. So it looks like that. And then in the second quadrant, tangent is negative, so at near pi over 2, it has an asymptote at negative infinity, or going down to negative infinity. The tangent of pi is 0 because it's sine over cosine. And then as tangent approaches 3 pi over 2, it has another asymptote. So that's what the graph of tangent x looks like. It has, oops, that should be in blue because I'm drawing my tangent graph in blue. So tangent x has zeros at 0, pi, 2 pi, and so on. It has asymptotes basically at the places where you're trying to divide by 0. And those are all the places where the cosine is 0, because remember tangent is sine over cosine. So those are at pi over 2, 3 pi over 2, and so on. So that's what the tangent function looks like. Now let me try to graph the cotangent function. Now the cotangent function, remember that's cosine over sine. So that has asymptotes and zeros, exactly the opposite of where tangent did. It has zeros wherever cosine is 0, which is pi over 2, 3 pi over 2, and so on. because cosine is 0 at those places. 3 pi over 2, 5 pi over 2. It has asymptotes wherever sine is 0 because we're trying to divide by 0. And that's 0, pi, 2 pi, and so on. So cotangent looks kind of just the opposite of tangent. Like that. So that's the cotangent function in red. For our next example, we're going to look at some right-angle triangles and try to work out some trigonometry there. So we're given that a right triangle has short sides of length 3 and 4. 3 and 4. And we're trying to find the tangents and cotangents of all the angles in the triangle. So the first thing we need to do is figure out what the hypotenuse of this triangle is. So we know that the hypotenuse squared is 3 squared plus 4 squared, which is 9 plus 16, which is 25. So the hypotenuse must be 5 units long. So let me figure out, first of all, the tangents of all the angles in the triangle. And we're going to use SOHCAHTOA. Remember, tangent equals opposite over adjacent. So the tangent of theta is the opposite over the adjacent, which is 3 over 4. The tangent of phi is the opposite side of phi, which is 4 over 3. And then the last angle in the triangle is 90 degrees. So that's the tangent of pi over 2 radians. But remember, the tangent is undefined for pi over 2. So I'm just going to leave that as undefined. That's because tangent is sine over cosine, and cosine of pi over 2 is 0. So now cotangent of each of these angles. Cotangent is just the opposite of tangent in the sense that when tangent is sine over cosine, cotangent is cosine over sine. So the cotangent of theta, instead of being 3 over 4, will be 4 over 3. And the cotangent of phi, instead of being 4 over 3, will be 3 over 4. And the cotangent of pi over 2, which is the cosine over the sine, so that's 0 over 1, is just 0. So the secret to working out tangents and cotangents of angles in right triangles is just to remember the SOHCAHTOA formula. In particular, the TOA part says tangent equals opposite over adjacent, so that quickly helps you figure out the tangents of angles in right triangles. For our next example, we're asked to determine if the tangent and cotangent functions are odd, even, or neither. And let's recall the definitions of odd and even functions. Odd function is where f of negative x is equal to negative f of x. Let me draw that a little more clearly. F of negative x is equal to negative f of x. And it's the kind of function that has rotational symmetry around the origin when you look at the graph. An even function satisfies f of negative x is just equal to f of x with no negative sign. and that has mirror symmetry across the y-axis. So those are the two definitions we want to check here. Let's try that out for tangent and cotangent. Tangent of negative x, let's see what happens. Well, tangent by definition is sine over cosine. So that's sine of negative x over cosine of negative x. Sine, remember, is an odd function. Sine of negative x is negative sine x. Cosine is an even function. So cosine of negative x is cosine x. And so you put this together, you get negative sine over cosine, so you get negative tangent of x. In particular, that tells you that tangent is odd. And we can check that with the graph of tangent. It's probably worth memorizing what the graph of tangent looks like. So the graph of tangent looked like this. It crosses right at the origin, crosses the x-axis right at the origin. And then it has asymptotes at negative pi over 2 and pi over 2. In particular, the graph of tangent has rotational symmetry around the origin. If you spun it around 180 degrees, it would look exactly the same. So it has that rotational symmetry around the origin. The graph of tangent definitely confirms that tangent is an odd function. Let's check that out for cotangent. Cotangent of negative x. Cotangent is just cosine over sine. So that's cosine of negative x over sine of negative x. Just like before, cosine of negative x is cosine x, because cosine is an even function. Sine of negative x is negative sine x. And so what we get is negative cosine over sine, negative cotangent x. So cotangent is odd also. It's also an odd function. And again, we can check that looking at the graph. So let me draw a quick graph of cotangent x. Again, probably worth remembering, but not quite as essential as the tangent function. So if you're going to remember one of them, remember the graph of the tangent function. But the cotangent function looks like this. It crosses 0 at pi over 2, and then it has asymptotes at 0 and pi. So again, the cotangent function, if you draw a dot on the origin and then rotate the thing 180 degrees, if you rotate the thing 180 degrees around the origin, the graph would look the same. So it has this mirror symmetry, or sorry, not mirror symmetry, but rotational symmetry around the origin. And so the cotangent function is an odd function. It does not have mirror symmetry, because if you flipped it across a mirror on the y-axis, it would not look the same. So it's not an even function, but it does have that rotational symmetry around the origin. So we've got another couple of examples coming up later. Why don't you try them out, and then we'll work them out together. Okay, another example of cotangents and tangents. We're given some common values here, 5 pi over 6, 5 pi over 4, and 5 pi over 3. So those are all angles on the unit circle, and we want to figure out what the tangents and the cotangents are. So a good way to start this is to draw the unit circle and to figure out where those angles are . So there's my unit circle, and let me label some easy common values. There's 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the angles we're being asked to find, 5 pi over 6 is just a little bit short of pi. 5 pi over 4 is in between pi and 3 pi over 2. And 5 pi over 3 is 5/6 of the way around the unit circle. It's down there. So those are the three angles we're being asked to find. And it's probably easiest if we just write down the sines and cosines of those angles, because presumably we know those pretty well, and then we can figure out the tangent and the cotangent. So let's make a little chart here. Well, I'll find the angle, I'll find the sine and the cosine. And then we'll find the tangent just by dividing those together, and the cotangent. So if we start with 5 pi over 6, that's this angle right here. And remember the common values here. The sine is the small one, so that's 1/2, and it's positive. Cosine is the bigger one, square root of 3 over 2, so that's negative because the x value is negative there. The tangent is sine over cosine, so that's 1 over the square root of 3, which rationalizes to square root of 3 over 3. And it's negative because the cosine was negative. And the cotangent is just cosine over sine, so that's root 3. And that's also negative. Now 5 pi over 4, that's a 45-degree angle south of the x-axis. So the sine and the cosine, because it's 45 degrees, they're both root 2 over 2. But we got to figure out whether they're positive or negative. And since it's in the third quadrant there, they're both negative. But that means when you divide them together to get the tangent, you get positive 1. And when you take the cotangent, you also get positive 1. Now 5 pi over 3, that's another 30, 60, 90-degree angle down here. Sine, the y value is the big one this time, so it's root 3 over 2. Cosine is 1/2. The sine is negative because we're still south of the x-axis, but the cosine is positive because we're to the right of the y-axis, meaning the x value is positive. Tangent is sine over cosine, so that's root 3, and that's negative. And the cotangent is cosine over sine, so that's 1 over root 3. So that rationalizes to root 3 over 3. And that's also negative. So those are our answers right there. And let me just emphasize that the key to figuring this problem out is to remember the sines and cosines using the common values in those common 30, 60, 90 triangles and the 45, 45, 90 triangles. As long as you remember those common values, then you can work out the sines and cosines, figure out which ones are positive and which ones are negative, and then divide them together to get the tangents and cotangents. And of course, it helps if you remember that the common values for tangent and cotangent, they're always going to be 1 and square root of 3 and square root of 3 over 3. And so it's just a matter of figuring out where they're positive and where they're negative and which is which for any given angle.